For as long as human beings have looked up at the night sky, we have imagined traveling among the stars. Ancient civilizations told stories of gods crossing the heavens. Modern science fiction shows humanity jumping effortlessly between galaxies, exploring alien worlds, and building civilizations beyond Earth. From Interstellar to Star Trek, interstellar travel feels not only possible, but inevitable. But when we move from imagination to physics, something unsettling happens. The universe, it turns out, may not be built for easy travel between stars at all. In fact, the deeper physicists look into the laws of nature, the clearer it becomes that interstellar travel is not just difficult. It may be fundamentally impossible with any technology allowed by known physics. And the reason is not engineering, fuel, or money. The real obstacle lies in the very structure of space, time, and energy itself. This is the story of why the universe seems to resist our attempts to cross it. The immense scale of space, the first problem is scale, and human intuition completely fails here. The moon feels far away at about 384,000 kilometers from Earth. Mars, at its closest, is tens of millions of kilometers away. These distances already challenge our best spacecraft. But compared to interstellar space, they're almost nothing. The nearest star system, Alpha Centauri, is about 4.37 light years away. A light! Year is the distance light travels in 1 year, about 9.46 trillion kilometers. That means even light, the fastest thing in the universe, takes more than 4 years to get there. Now consider this, the fastest human-made object ever created, NASA's Parker Solar Probe, travels at about 700,000 kilometers per each hour. That sounds incredibly fast. Until you realize it would still take over 6,000 years to reach Alpha Centauri. 6,000 years, that's longer than recorded human history. And this is just the nearest star. Most stars are tens, hundreds, or thousands of light years away. The Milky Way galaxy itself is about 100,000 light years across. Even if humanity survived long enough, even if technology improved dramatically, the distances alone create a problem, so enormous that it begins to look less like a technical challenge and more like a physical boundary. But distance alone is not what makes interstellar travel nearly impossible. The real barrier is speed, the cosmic speed limit in everyday life. Speed feels flexible. Cars go faster than bicycles, planes go faster than cars, rockets go faster than planes. So it seems reasonable to assume that eventually we could just keep going faster and faster until reaching the stars quickly. Physics says otherwise. According to Einstein's theory of relativity, the speed of light, about 299,792 kilometers per second, is not just fast, it is the maximum speed at which information or matter can travel through space. Nothing with mass can reach or exceed this speed, and the reason is deeply strange. As an object moves faster, its energy increases. But that energy doesn't just make it go faster. Instead, it increases the object's relativistic mass, meaning it becomes harder and harder to accelerate further. The closer you get to the speed of light, the more energy you need for even a tiny increase in speed. Near light speed, the required energy approaches infinity. In other words, reaching light speed would require infinite energy, something physically impossible. This is not a technological limitation. It's not something we can fix with better engines or stronger materials. It is built directly into the structure of space-time itself. The universe has a speed limit, and it is absolute. This alone changes everything about interstellar travel. Even reaching 10% of light speed, unimaginably fast by human standards, would require enormous energy far beyond what humanity currently produces. And even then, the journey to nearby stars would still take decades. Energy, the hidden enemy to understand the scale of the problem. Consider energy requirements. The kinetic energy of an object increases with the square of its velocity. Double the speed, and you need 4 times the energy. Increase speed tenfold, and energy requirements increase 100 times. Now imagine accelerating a spacecraft large enough to carry humans, life support systems, shielding, food, and fuel. At relativistic speeds, the energy required becomes comparable to the total energy output of entire nations, or even planets. And that's just acceleration. You also need energy to slow down when you arrive. Otherwise, you would simply fly past your destination at enormous speed. This doubles the energy problem. Then comes shielding. Space is not empty. Tiny dust particles become deadly at high velocities. At a significant fraction of light speed, even microscopic grains impact with explosive force, releasing energy comparable to bullets or explosives. A spacecraft traveling between stars would need massive protection, increasing weight, which increases energy requirements even further. Every solution creates a new problem. Physics begins to close in from all sides. Time, the strange twist relativity, introduces one more strange effect. Time dilation. From the perspective of travelers moving close to light speed, time slows down. A journey that takes decades on Earth might feel like only a few years on board the ship. This sounds like a solution, and science fiction often presents it as one, but time dilation does not solve the energy problem. To reach those speeds, you still need enormous energy, and while travelers might age slowly, everyone on Earth continues aging normally. A crew could arrive at a distant star only to find centuries have passed at home. Interstellar travel becomes not just a journey through space, but a one-way trip through time. Civilizations, languages, and even humanity itself might change before travelers return. The stars begin to feel less like destinations and more like separate universes. The emerging realization when physicists combine these factors, distance, the speed of light, energy requirements, and relativistic effects, a sobering conclusion emerges. The universe may not forbid interstellar travel outright, but it makes it so extraordinarily difficult that practical, routine travel between stars may never be achievable for biological civilizations like ours. The laws of physics do not say no. They simply make the cost unimaginably high. And this raises a haunting question. If interstellar travel is this hard for us, could it also be impossible for everyone else? Could this be one reason the universe appears silent? In science fiction, the solution to interstellar travel seems simple. If the universe is too big and the speed of light is too slow, then the answer must be to go faster than light. Warp drives bend space. Wormholes connect distant stars. Hyperspace allows ships to jump across galaxies in seconds. These ideas are exciting, imaginative, and deeply appealing. But when physicists examine them carefully, something strange happens. The problem is not just that faster than light travel is difficult. The problem is that it appears to break the fundamental logic of reality itself. To understand why, we need to look deeper into what space and time actually are. Space and time are not separate before Einstein. Space and time were thought to be independent. Space was the stage where events happened, and time flowed equally for everyone, everywhere. Motion simply meant moving through space as time ticked forward. Relativity changed everything. Einstein showed that space and time form a single unified structure called space-time. Moving through space affects how you move through time, and vice versa. The faster you move through space, the slower time passes for you relative to others. This is not philosophy. It has been experimentally confirmed countless times. Atomic clocks on airplanes run slightly slower than clocks on Earth. GPS satellites must correct for relativistic time differences to function properly. The universe is not just a place, it is a geometric structure, and within that structure, the speed of light acts as a boundary, not just for motion, but for cause and effect. The speed of light protects causality. One of the deepest reasons faster than light travel is forbidden is something called causality, the principle that causes happen before effects. If faster than light travel were possible, this order could be reversed. Imagine sending a message faster than light. Because different observers experience time differently depending on their motion, there are situations where another observer could receive the message before it was sent. This is not science fiction speculation. It emerges directly from the mathematics of relativity. In such a universe, paradoxes become unavoidable. You could warn someone about an event before it happened, potentially preventing the event that caused the warning in the first place. The logical structure of reality begins to collapse. The speed of light, in this sense, acts like a safety mechanism. It preserves the order of events across the universe. Breaking the light speed barrier doesn't just mean going faster. It means risking a universe where time loops and contradictions exist. Physics strongly resists this possibility. Warp drives, a mathematical trick with a fatal problem. One of the most famous attempts to bypass the speed limit is the Alcubierre warp drive, proposed in 1994. The idea is clever. Instead of moving a spacecraft through space faster than light, you move space itself. Space in front of the ship contracts, and space behind it expands, carrying the ship along like a wave. Locally, the ship never exceeds light speed, but globally it could travel faster than light relative to distant observers. At first glance, This seems like a loophole. General relativity allows space-time itself to stretch faster than light. The expansion of the universe already does this. So why not engineer a local version? The problem is energy. The equations require a form of negative energy density, often called exotic matter. This is not just unusual material. It is something that may not exist in usable quantities at all. Known physics allows tiny negative energy effects at quantum scales, but nothing remotely close to what a warp drive would require. Early estimates suggested energy equivalent to the mass of Jupiter. Later refinements reduced it, but still to absurdly large amounts, comparable to planetary or stellar energy scales. And even if exotic matter existed, new problems appear. Some calculations suggest warp bubbles would generate catastrophic radiation when turning off, potentially destroying the destination itself. The warp drive, while mathematically fascinating, appears physically unreachable. Wormholes, shortcuts. That collapse another popular idea is the wormhole, a shortcut connecting two distant points in space-time. Instead of traveling across space, you simply step through a tunnel. Einstein's equations allow such structures in theory. In fact, solutions resembling wormholes appear naturally in general relativity. But again, physics introduces a catch. Wormholes appear to be inherently unstable the moment matter enters them. Gravitational effects cause them to collapse instantly. To keep a wormhole open, you would again need exotic negative energy. And even worse, stable wormholes may allow time travel, reintroducing causality violations. Many physicists suspect that unknown laws of quantum gravity prevent macroscopic wormholes from existing at all. A concept sometimes called the chronology protection conjecture, proposed by Stephen Hawking. In simple terms, the universe may actively prevent time paradoxes by making wormholes impossible to use. Quantum physics does not save us some hope that quantum mechanics might provide a way around relativity. After all, quantum particles can appear to influence each other instantly through entanglement, but entanglement cannot transmit information faster than light. No usable signal travels between entangled particles. The speed of light limit remains intact. Even speculative ideas like quantum tunneling do not allow faster than light communication or travel. Quantum physics, instead of breaking relativity, seems to reinforce its limits. The deeper we look, the more consistent the cosmic speed limit becomes. The universe may be designed for isolation. When all these ideas are examined together, an uncomfortable picture emerges. The laws of physics allow stars to form, planets to exist, and life to evolve. But they may also ensure that civilizations remain separated by vast, nearly uncrossable distances. Travel within solar systems may be achievable. Travel between stars may remain rare, slow, and enormously costly. Travel between galaxies may be effectively impossible. The universe is not empty because travel is easy. It may be empty because travel is too hard. And this leads to a profound realization. The silence we observe in the cosmos might not mean we are alone. It might mean that everyone is trapped by the same physical limits. By now, the picture seems almost hopeless. The distances between stars are enormous. The speed of light cannot be exceeded. Energy requirements grow beyond comprehension. Warp drives demand exotic matter that may not exist. Wormholes collapse before they can be used. Even quantum physics refuses to provide an escape route if the laws of physics are correct. And every experiment so far suggests they are. Then interstellar travel as imagined in science fiction may never happen. But impossibility in physics rarely means absolute impossibility. Instead, it often means something subtler. The universe forces us to change our expectations. The question is no longer, how do we travel to the stars quickly? The real question becomes, how do we exist in a universe where travel is slow? And this shift changes everything. Accepting the slow universe, human civilization evolved in a world where movement is fast compared to distance. You can cross continents in hours and communicate globally in seconds. Our psychology expects speed. The universe does not share this expectation. At cosmic scales, even light is slow. Signals between stars take years, between galaxies, millions of years. The universe operates on timescales far beyond human lifetime. If interstellar travel is ever achieved, it may not resemble exploration, missions, or heroic journeys. Instead, it may resemble migration, slow, irreversible, and spanning generations. This leads to one of the oldest serious ideas in interstellar physics, the generation ship. Generation ships, civilizations in motion. A generation ship does not attempt to defeat physics. It accepts it. instead of transporting travelers who expect to arrive within their own lifetimes. A generation ship becomes a self-contained world. The people who launch it know they will never reach the destination. Their children, or their children's children, will arrive centuries later. In theory, this avoids the need for near-light speed travel. Even a spacecraft traveling at a small fraction of light speed could eventually reach nearby stars. But this introduces new challenges, many of them not technological but human. A generation ship must sustain life for centuries without failure. Ecosystems must remain stable. Social structures must survive isolation. Knowledge must be preserved without degradation. Psychological stability becomes as important as engineering. The ship stops being a vehicle and becomes a civilization. And history shows that civilizations change. Cultures evolve. Priorities shift. After several generations, would the inhabitants even remember or care about the original mission? The physics problem transforms into a sociological one. Suspended time, the dream of sleeping through the journey, another idea, attempts to preserve the human experience of travel. Suspended animation or cryogenic sleep. If humans could safely slow or stop biological aging, travelers might survive journeys lasting centuries from an external perspective, while experiencing only a short passage of time. Unlike faster than light travel, this does not violate physics. Time dilation already shows that time itself is flexible. However, biology presents enormous challenges. Freezing complex organisms without damage, preventing cellular decay, and safely restarting life processes remain unsolved problems. Even small errors could be fatal. Yet among all proposed solutions, suspended animation may be one of the most realistic. It does not fight physics. It works within it. The universe remains slow. We simply wait different. Machines instead of humans, there is another possibility, one that many physicists consider more likely. Perhaps humans themselves will never travel between stars. Machines might. Robotic probes do not require oxygen, food, or psychological comfort. They can travel for thousands of years if built robustly enough. Artificial intelligence could explore distant systems, send back information, or even construct habitats before humans ever arrive. In this scenario, interstellar exploration becomes less about movement and more about communication and expansion of knowledge. Humanity spreads its presence indirectly through technology rather than biology. This may sound less romantic than starships full of explorers, but it aligns far better with known physics. The unknown frontier, new physics history teaches us humility. Newton believed his laws described everything until relativity and quantum mechanics revealed deeper layers of reality. It is possible that future discoveries could change our understanding again. A complete theory of quantum gravity might reveal new phenomena. Unknown properties of space-time could exist. Concepts like higher dimensions or new energy states remain speculative, but not entirely ruled out. However, physicists are cautious for a reason. Every time we have expanded our understanding of nature, new laws have not made the universe easier to navigate. They have often revealed deeper limits. Relativity did not make travel faster. It introduced speed limits. Quantum mechanics did not make reality predictable. It introduced uncertainty. Future physics may not free us from limitations. It may explain why they exist. A different kind of destiny, perhaps the most profound realization, is this. Interstellar travel may be impossible, not because the universe is hostile, but because it is vast. The cosmos may not be meant to be crossed quickly. Civilizations may be local phenomena, growing around their own stars, separated by immense distances and times. If this is true, humanity's future may not lie in conquering the galaxy, but in understanding and preserving the small corner of it we inhabit. The dream of the stars then changes meaning. Instead of destinations, stars become reminders of scale, evidence that reality is larger and stranger than our ambitions. And yet, impossibility has never stopped curiosity. Even if we never reach another star, the attempt itself reshapes science, technology, and philosophy. The journey toward understanding becomes as important as the journey through space. The universe may limit our movement, but it does not limit our imagination.